So I think students were missing today. What do you think about your exam last Tuesday? Pressurized. How about the question? How much you can do? 70% or 75? Around. I think which one is the most makes you in trouble? The last one. Last one. Okay. Okay. Hopefully next Tuesday or Thursday maybe it will finish. So just keep for a moment, and hopefully there will be no makeup exam. Okay. Okay. So today's class, I would like just to continue what we have been doing so far in partial derivatives. So this is actually the limit definition of partial derivative that we are going to elaborate and discuss. So if you remember in calculus 1, we have limit definition, right, in the derivative. So now, to make sure that we know the partial derivative, and we have taken the approach for limit, taken for, if we have two variables, we can make one of the variable as a constant, and that is how we define which one is which. So for example, if we say that we are going to partial derive with respect to x, it means that the variable y is a constant. So if you can see the structure that is going to be changed is only the x. The y is just a constant. And for the partial derivative with respect to y at the point AB, the one that changed is y. And all the components in the limit definition, they are all the same. Okay. Usually, if you remember calculus 1, we have this is perhaps this x. This is x plus h, x plus h, right? And then this is f of x, and this is h. But now we have 2 points. We have 2 points A, B, x, y. That means we can have this or this. Depends in which we can make a derivative with. If we make derivative with x, it means that the change on the x. If we make derivative with y, it means the change is in y. Okay. So if we let me check here. Okay, so then we could write this 2 as our limit definition for both partial derivative with respect to x and with respect to y. Okay, so this is we call this we call this is partial derivative of f with respect to x. Okay. And the same thing for this one. This will be partial derivative of f with respect to y. Okay. And how to write the notations? We can write the notation of partial derivative as this one. So take a small f and you take the subscript of the variable y and x for two variables. And we can have also, if we have like a more than 2, like 3, 4, 5, we can have, but I think for now, let me just explain in 2 variables to make it easy to comprehend. And another notation that might be possible that usually we write, we can write in terms of the point, we can include the point, or just normally partial derivative with respect to x like this, or using the Leibniz notation. This is called the Leibniz notation, or Leibniz and then maybe xy. Basically, it's just the same thing. Or even you can write using the d subscript 1f. This means that 1 is referring to x and 2 is referring to y. But usually, I would like just to write in my course using this or this, okay? Just this two, okay? Most of the time, okay, most of the time. And how exactly we are going to find the partial derivatives in practical way, So in practice, if we want to find partial x, it means that if we look at the limit definition, partial x means that the only way to change is the x. Y is a constant, which means when we derive the equation, we treat y as a constant. Okay? So for example, I'm just using the example here. For example, if we have the f xy, let's just define this as x cubed plus x squared y cubed minus 2y squared. And if we want to find the partial x, it means we are going to derive all this component with respect to x. And we are going to treat variable y as a constant, which means this will be 3x squared, and this will be 2x, and y cubed is we keep as a constant. This is y cubed. So we can write then. So 3x squared plus 2x y cubed. Okay. So y cubed is just as constant. And how about y squared? Since y squared treat as a constant, then it will be 0. Okay. Just like any normal numbers. Okay. So this is the partial derivative with respect to x. Okay. Now, what will happen if we have partial with respect to y? Now, we're going to treat the x as a constant, and y, we are going to derive the y. Okay. So y cubed becomes 3y squared, and x squared. So I'll write 3x squared y squared. Okay. And the x cubed will be 0. So this will be 3x squared y squared minus 4y. Okay. So this one now, we derive y, and we keep x as a constant. Remember, we keep x as a constant. Like any regular numbers, every time you have only constant, if you derive, it will be a 0. That means the x cubed here is 0. Okay? So far, so good, right? I hope this could be understood very well, because it's very practical. It will be very different if we have another function that is maybe more. But I hope this part can be comprehended. Okay. Now let's say we have another function g, and let's include the trigonometric. Okay, now we have sine, and then inside the function is x over 1 plus 1. Now we make it a little complicated a little bit. So sine, I have here is the two variables, x and y. If you would like to partially derive with respect to x, if you remember the chain rule that we have in calculus 1, we might apply it as well. Although later we have another chain rule in our partial derivative. We are not yet on to the chain rule in partial derivative, but we can use chain rule in calculus 1. Right? So if we have sine holding here, it doesn't matter what kind of function is sine. We can just derive this, it becomes cosine, right? So let's just derive that. So actually, this will be cosine And I will write all the things the same, just the same as the original function. And then I will multiply with my Leibniz of the x of the inside function, right? And now we are making this as we did with this. So we are going to derive with respect to x and treat y as a constant, which means this will be this 1, right? 1 over 1 plus 1. So this will be cosine, right? And then this will be multiplied with 1 over 1 plus y. Now taking to the partial derivative y, it will be the same cosine x over 1 plus y, and then taking another Leibniz for y, okay. Now what will happen? Now x is a constant. But we need to derive the 1 over 1 plus 1. We could just take it up here, and it will be 1 plus y, negative 1. Negative 1, it will be negative 2. And then go to the front, is negative. So negative 1 plus y is power of negative 2. Okay. So let me just write that for you. So this means that I will write here I will just make it into d, just to let you know how we did this. So negative 1 plus y, negative 2, right? Or it will be negative 1 over 1 plus y squared. Okay. And then we multiply the x since it's a constant. Okay. And since it's negative, I will write the negative in the front. So let me shift this to the right. So negative, and this will be 1, or rather multiply with x over 1 plus y, and then square. Okay. Okay, I will erase this part. Okay, so far so good. Let me give you another function. It's 1, 2, 3. Okay, let me give you another functions. Let's say we have not f, maybe h. Suppose that we have x and then e, and then we have x squared y as a power. I will write the complete questions that you need to compute. Evaluate partial x, partial y at a certain point that we decide this will be 1, ln 2. So for each x and y. Well, actually, this is not f. This should be g. Okay. I'm writing f to make sure that you understand that all these are partial derivatives. Okay, so now the question is still the same. Okay, so maybe this is not f. It should be h. But I hope you understand why. Now we have xe with power of x squared 1. Notice that only variable x that have in these two components, right? Which means that when you multiply this and you derive, if you want to derive with respect to x, then it will be a product. It's a product rule in derivative, which means we are going to take the product rule in derivative. Product rule is if we have fg, then the product rule will give you these definitions. So let me write the age x, which means the partial x or partial derivative with respect to x. This will give you make it bigger plus x and then multiply with 2x e x squared y, or okay. Oh, I forgot to write y. Should be okay. Remember, y is a constant that we need to keep as it is, right? So think about this first. I hope you get this correctly. So we have two components, which we are going to derive in a product rule method. If you have f g, this will be f prime g plus g prime f, right? So here, first I will derive x, and then this is as it is, which is the first one. And the second part here, I will just keep x as it is and derive this. And how to derive the e will be the e and then chain rule of this x squared one, which is only x, because this is only derivable in x. So this will be 2xy. So 2xy e. Multiply and we get 3. Okay? I hope you get it. Okay, anyone still have confusion about this one? About the product rules? Okay. Just take it slowly. Make sure that you derive the first component, keep at this the second one, and then the second one derive, and then multiply the first. That's it. The same thing with this. Okay? But now we mix up with the partial derivative, which, if we have two variables, we need to know which one that needs to be derived. This is only x. So y is just keep like a number. So if you change y with 2 or 3, this will be 3 or 2 or 1, whatever, right? It's like a regular number. That's how the partial derivative works. Okay, now if we see the partial derivative of y with respect to y, notice that we only have y on the second component. It means that we just derive this e, okay, and keep x as a constant. Okay? So this will be derived. So e x squared y will be derived as x squared e. Okay? So this will be x, and then multiply with x squared e x squared y, or x cubed e x squared y, or maybe too small. Okay. But the questions need to be also answered. We need to compute this. So we put x equal 1 and put ln2 within these two calculations. So let me write on the right side. So this will be 1 ln2. So I will put everything e ln2 plus 2 ln2 e ln2. So this will be 2, this will be 2, right? So this will be 2 plus 2. So this will be 4, right? 4 ln 2, right? And the hy is just 1, and then e ln 2, or this is just 2. Okay, so that's it. Okay, so far we can derive partially with respect to x or with respect to y. And of course, if we could increase to more than 2 variables, there will be slightly similar. It will be slightly similar. The differences depends on our definition of the function itself. I will explain in detail later. But anyway, any question for this one? Okay. Since this is very practical and we are going to deal with this regularly, I hope you get this comprehensions correctly. If you miss out this, the rest of the chapter will be very difficult. Okay. Okay, now so far we discussed practice applications and some limit definition, but we are not sure yet how we could describe the partial derivative in a graph or in visuals. How do we imagine the partial derivative? If you remember calculus 1, we described the derivative as a tangent. It's easily to draw the line, right, in the curve. But here, in summary, in the conclusion, I will say what we have is actually a plane. So instead of just a line, in 3 dimensions we have a plane, okay, which will be depends on the surface, the points on the surface. So suppose this is a surface like that. In every point, you can make a plane. Depends on the point, right? And that plane is the one that we need to visualize and describe, okay, throughout this definition. So let me explain that after this page. Okay. Okay, so let me go through the next page. I hope you have done this part. So this is geometric interpretations. So let me write something just to make sure that we have the same idea. So let's say we have a function. So recall we have a functions that describe by z is actually function of 2 variables x, y, okay? Which this is going to represent this functions. It's representing surface. The surface S, okay? In the picture you have S, right? And the point P at the point ABC is on the surface, right? And if we take y equal b, it means that if you see this is AB0, okay? So if we take y equal b, it means that we're going to take the all the movement is only on the C1. This is the y equal b. Let me just write that. This is b. This is x equal a. So if y equal b, then it means we restrict observation to C1. Okay, if you see the curve C1 in the surface, okay, and if we let x equal a, then we restrict the observations to C2, okay? And both curves, both C1 and C2, they both passing point P, right? Which is on the ABC point. This curve C1, based on our definitions previously, in limit definitions, this is, let me rename this as a functions g of x, which is f x b. Okay, y is a constant b, okay, from the surface functions. And the C2, this will be hy, okay. And now, from these two curves, if you see the picture, we have a line. So if you see from this side, you can see that this is just a normal curve, and this is a line, like in calculus 1. So the T1 is actually the derivative of this curve, right, at that point. Okay? And the same way, we can also view C2 only in ZY axis, only these two axes. And we can see that this C2 at this point have a derivative of this, right, the T2. So we can write, within these terms, we can write that T1 is actually G prime, because this is only x, our variable is only x, right? That will be derived. B is just a constant. So this will be the tangent, or the derivative will be G prime at the point A, right? At the point A. Or we could write this in partial symbols. This is the partial derivative with respect to x at AB. The same thing with the T2. This will be H prime B, and this will be, okay. So this is these two curves is helping us to describe each view into one single variable definition, okay? Like when we did in calculus 1. And then, based on our definition in partial derivative, we can make that into these two definitions. So actually, the plane that we might come will be defined based on the C1 and T2. Okay? So I can write here, maybe let me just write, maybe put here over there. Okay, let me write conclusions here that the partial xab and partial yab can be interpreted geometrically as the slopes of the tangent lines at point P, ABC, to the traces of C1 and C2 of surface S. Maybe let me make with a different color. in planes y equal b and x equal a. Okay, later we are going to describe after this, I think after this topics, we're going to describe the T1 and T2, both of the lines. It will make a plane, which we call a tangent plane, but I think that will be after this part. So I would like to give you some approach first on some sample surface. Let me just write the sample surface example here. So suppose that we have f is 4 minus x squared minus y squared, and we need to find the partial derivative for both x and y at the same point 1, 1. Okay, so remember, in partial derivative, this will be negative 2x, and partial y will be negative 2y. Okay. Oh wait, wrong functions, not complete. So 2y squared, right? Okay. Now this will be negative 4y, and plug in 1, 1, plug in 1, 1. This will be just negative 2, this will be negative 4. And what does this mean? What does this mean? This surface, this is what we call the paraboloid, right? The paraboloid. We can write this as z 4 minus x squared minus 2y squared. We can have a two different parabola from each side if we take z equal 0, or if we take x or y equal 0. It could be z equal 4 minus 2y squared, or z equal 4 minus x squared, which both of this curve will be a parabola, right, for both views. So then we have this. You could see, what does it mean? It means that these two, when x equal 1 or when y equal 1 as a constant, which means if we have this, which means that this will be the partial x. This will be the partial x, because y is a constant, and this will be the partial y. So partial y is on, if we see from this side, is on the zy axis, and the partial x is on the xz axis. Xz axis, y is a constant. Okay? Remember that this is, I think you will see this is very often. This is partial y, partial derivative with respect to y. And you see the zy axis because y is the one changing. Z is also changing because y is changing. And x is constant. Right? This is also similar. Y is constant. The one that's changed is x and also z. And we can also represent the partial derivative as rate of change. Okay, let me write here. We can represent a partial derivatives as a rate of change, just similar to what we have in calculus 1. So if z is fxy, then when we have the dodo x z, this represents rate of change of z with respect to x and y is fixed constant. Okay. Now, if we have more than two variables, we can still define them in limit definitions, but the problem is when we try to define in geometric perspective, because it will be very difficult. If we have like 4 dimension or 5th dimension, it will be very difficult to draw and to imagine, right? Yeah. So, for example, let me just write this, just some notes here, small notes that we can expand after this part. So this will be, let me write here, functions of 3 or more variables. So idea, let me just write the limit definitions. So if you have the partial x on x, y, z, suppose that w is our new functions of 3 variables x, y, z. So if you have the partial x, means that x is change, and we have y, we have z, and we have minus x, y, z. This can be found by taking y and z as a constant. But we are difficult to define in geometry. And the same way, if you want to partially derive with y, then x and z will be a constant. Okay. So, as an example, in practice, so if you have f, x, y, z, let's say this is e, x, y, l, and z. So we have 3 variables now. And it will be the same way if we increase the number of variables. Maybe 4, 5, 6. It means that when we have partial derivative of with respect to x or y or z or whatever variables you have, you are going to treat the other part will be as a constant. Now, if we have this, and we are going to compute all the component for perhaps the partial x. Let's start with the partial x. Since this is only having x only in the e, then all the parts y and z, we can leave that as a constant. So we could just derive this only. This will be e with power of x, will be just, we take this as a chain rule, y, e, x, y, and then multiply it times z. Okay. Okay. And if we take partial y, the same way, because this has the same structure, but now we treat x and z as a constant. So we have x, e, x, y, and then l and z. And if we have partial z, then the xy will be a constant. So we could just leave e as it is and derive L and z, which you can find this will be 1 over z, right? So now you get the pattern. So if we have like more and more variables, as long as we know our direction, either we derive with respect to x, y, or z, we can just focus on this only and leave the other variables as a constant. Okay? Leave the other variables as a constant. Anyone still have any confusion or maybe some questions regarding the practical approach to deriving? I think it should be okay. Should be okay. I mean, in a concept, it should be okay. Although if we have different cases, it will be very different. That depends on the functions. Okay. So far, we only discuss the first derivative, right? In partial, we can have the higher order. We can have the second derivative, the third derivative, but since it's partial, we can have first partial with x and then partial with y. Or partial x and then partial x again, twice. We can have partial y and then partial x. So it depends on the order. And that's how we could know which one is which. Okay, I hope everyone finished these notes here. So we call this the higher derivatives. So if z is two variables x, y, so we start by two variables. Now, how we write our higher derivatives, okay, or this is supposed to be the second derivative in partials. We can write as fxx, which means we partial derive with x and then derive again once more with x. Okay, so twice x and then x. We can have xy. It means the first one is x and then the second one is with y. So this is already in order. So xx means the first x, the second x. xy means the first x, the second will be y. This will be yx and then yy. Okay? So this will be the order of our derivative. Okay? So you derive first with the first order, and then you derive the second variable. And of course, if you have like a higher order, maybe third derivative, it can be x, xy, xyx, and every order that you can define. And if you have like more than two variables, it can be xyz or xxy, xyz, and fourth derivative. But again, the principles will stay the same. This will be the order in which you are going to derive your functions. Okay. Just a small example, I hope maybe before the class break. So if we have fxy example. Okay, suppose we want to find fxx, fyx, xy, fyy. Now, of course, if this is the higher derivatives, the first thing you need to find is the first derivative, right? Either fx or fy, the partial x or partial y. And then derive one more, depends on which order you are going to be achieving. So first, maybe taking the partial x, this will be 3x squared, right? Plus 2x y cubed, and the other one will be a constant, 0. And then partial y, x cubed will be 0. This will be 3x squared y squared and this will be 4y, right? Now, based on these two partial derivative results, then we could further derive. Okay, so partial derivative xx, we are going to derive once more the partial x. Okay. Let me just one more here. Let me just write 6x plus 2y cubed. Okay. We are going to continue after the break. Okay. Okay, let's continue. So the next partial, we have partial yx. It means that we start from partial y and then taking another partial with x. So we are going to derive with respect to x our fy. Right? So this will be 6xy squared, and then the other part will be 0, right? Because it's only 4y. Okay. Now partial xy, then we start from partial x and then derive with respect to y. 3x squared becomes 0, and this will be 6xy squared. Okay, and the partial y, we describe this in 6x squared y, and then minus 4. Notice that the second part here and the third part, they are the same, right? So this is giving you a new concept that whenever you try to derive either from x and then y, and from y, from x to y, or from y to x, they have the same result. So it will be also work well with it if you have three variables. For example, x, y, x, it will be the same as x, x, y. This will be a concept called the Clairaut's. This will be a concept of Clairaut's theorem, that the fxy will be the same as fyx. The result of this partial will be the same. And basically that's the important part on the higher order. Okay, one small note. I think it will be different from the textbook a little bit. I will add within here a implicit partial. Okay, so if you remember, we have a concept of implicit in calculus 1. Let me rewrite the concept for you. Or maybe if you want to write this first, the Clairaut's. Okay, so in calculus 1, let me write here. In calculus 1, suppose that we have y is f of x, only one single variable in calculus 1, right? And then if we have, suppose that we have x squared plus 2y equal to x. We can immediately derive this implicitly. Implicitly means that we are going to take all of this with ddx. For variable x, no problem. We could just deal with them easily as usual. But for y, we are going to deal with this y as they are a function of x, which we are going to take this y, and they are going to be depends on this x, which result in dy dx. So this will be plus 2 dy dx and then equal to, and then we get easily our dy dx, right? This is in calculus 1. Now we can make this concept in calculus 2 using partial differentiation. It will be work similarly. The difference is we are dealing with a multivariable. In calculus 1, we only deal with a single variable. So now let me write here. So in calculus 2, we may have, let's say, function of two variable xy, our z. So we can have two possibilities. We can have d dx or Leibniz notations with respect to x or with respect to y. For example, if I wrote the questions, let me take this a little bit here. Let me wrote example, find slope in y direction of sphere x squared plus y squared plus z squared equal 1. So this is a sphere with a radius 1 at 2/3, 1/3, 2/3. Okay, you can ignore the numbers for now. Let's just focus on the question itself. The question is asking the slope in y direction, which means we are going to take the derivative with respect to y. Okay, remember that we did in the previous example. So this will be our functions. We can directly derive all of this with respect to y. Now, how to deal with the partial derivative? So since we take in y direction, it means that x will be a constant. So for sure this will be a 0 if you derive. This will be same, so 2y. And the z, since z is connected to this, then the z will be, we derive this and multiply with the dy or dz dy, just like we did in calculus 1. Okay? So this will be 0 plus 2y plus 2z, and then dou z dou y equal 0. And again, we get dou z dou y. This will be minus y over z. And since the question need to include the point, then we need to compute that as in the given points. So we input at the point which equals 1/3 divided by 2/3 is 1/2, so negative 1/2. So as long as you know which one is the constant for these three variables, for example, if y is constant, so this will be a 0, this will be 2x, and this is dou z dou x, if we take this with respect to x. And if we have more, then we need to make sure that we can define all the variables. Which one is the constant, which one is the one that is changing. And of course, if we take z as a function of two variables, it means that z indirectly will have dependency on each one of them. if x is constant, so 0 depends on how y will be changing. That's why we have this dz dt, partially or implicitly. Okay. Okay, let's continue. So this is all the subtopics on techniques in partial derivative. So we know the limit definitions. We know practically how to derive partially. We can visually interpret the partial derivative in graphs. And then we have the higher order, when we have like a more than, like, it's not only the first derivative, it can be second order or the third order as well. And if we take more variables, we can still make partial derivative as long as we know which one we need to derive, which variable. Okay. So the next part will be the continuations of the graphs. So we are going to see the tangent planes that we are going to that we want to achieve. So this next part will be the tangent planes and linear approximations. Okay, so far, as we did in the previous slides, that we might have these two lines that we define this line as our slope, right? The slope or the partial derivative with respect to x and with respect to y. So now we can define this as the tangent plane to the, let's say this is the surface S, okay, to the surface, this one, S. Surface S at point P is going to be defined the plane that contains tangent lines T1 and T2. And thus, at P, let's say P initial point is x0, y0, z0, the plane equation will be a x minus x0 plus b. This is standard form of any plane equation in 3 dimensions, plus c z minus z0 equals 0. Okay. Okay. Now we would like to make this divide by c. Okay, let's just divide by c. So the whole will be multiplied with 1 over c, so that this will be a over c. This will be this one. And let's move all the components. So the left side equations will be z minus z0, and I will move this component to the right side. Okay. And to make it easy, I will rename this a over c and b over c as a and b. So this will be z minus z0. This will be a. Or let me write with a different color. A and then plus b. Okay. Okay, and then let y equal y0. This will be give you z minus z0 is equal with a x minus x0, and the other component will be 0 at y equal y0. And then let x equal x0, which means you have only b for the y component. Now these two, I think I will move this a little bit to the left and this to the right side here. So I will rewrite this and simplify it as in A. This will be z minus z0 minus x minus x0. So this is giving you intuitively giving you the descriptions, the change in z and the change in x. Or if you say this is a delta, this is a delta, which means this is the gradient or the slope. So this will be giving you the idea that this will be equal to this. So this will be the T1. Same thing here with B. You have dou z dou y, which is partial y. So this will be T2 partial with respect to y. And then this is our conclusions for our tangent plane. Okay. So the equation of tangent plane, suppose that f is continuous partially, and the equation of the tangent plane for the surface z equal fxy at the point P, x0, y0, z0. It means that this will be z minus z0 equal partial x at this point xy, multiply with x minus x0, partial y at the x and y at the point y minus y0. Okay. So this is a standard equation for the tangent plane. You will see that as we progress, there will be some other ways to describe the tangent plane. You can you can see which one is suitable. And I think if you see the progress, the more we have in the chapters, we can see that actually it will be very easy to describe the tangent plane. Now, what we describe here, as long as we know that the z is function two variables, then the difference in this z will be equal to this partial x minus x0, partial y minus y0. This partial x, partial y, of course, it will be the tangent or the slope of the tangent line. For what?
To find the equation of the tangent.
No need. You can directly use. Remember in calculus 1, just to mention that this is actually similar. In calculus 1, we have y minus y0 equal f prime at x at some point, multiply x minus x0. Done. But now we have z minus z0, and we have two components that we need to deal with, which is practically very similar. This is going to be the first derivative, right? This is also the first derivative with partial. In calculus 1, you have also the first derivative. Maybe let me write in here. Note that here in cal 1, right? This means you need to put in the value to get the tangent or the slope of the tangent. Okay, just one more here, just to make sure that we get the point here. So let's say we have the example here, just similar with the textbook. So we have the elliptic paraboloid, which means at a certain point it will be an ellipse. You see from the one side, and in another side we are going to see the paraboloid. We are going to see parabola z equal to x squared and z equal to y squared, right? In the sides. If we see from the top-down view, the xy plane, we see the ellipse. Okay. But here, what we need to find is the tangent plane. Okay, so what we need to do? First, we see the describable functions is a function of two variables x1. So we see that this will be z equal fxy, which means that we can find the partial x and partial y. And basically, since we have the point 1, 1, 3, we are going to use this point as our x0, y0, z0. Right? So write down so suppose that z is fxy. So the partial x will be 4x, right? And partial y will be 2y. And taking the point as 1, 1, 3, or you could just put x equal 1 because there's no y and z. This will be giving you 4, this will be giving you 2. I think very simple. And we can write z minus z0 equal partial x this is 1, 1, and then this will be, or maybe let me just write the whole formula. For if you want to complete this, for x plus 2y minus 4 minus 2 minus 6 plus 3, and this will be the plane equations. Notice that this is the picture for our elliptic paraboloid. And this is our tangent plane. And of course, here is the 1, 1, 3. So this is 1, 1, 3 is going to be this one here. And what does it do? If you see from this 3 picture, is if we take zoom in this part, we're going to see that the gaps between the surface and the plane, if we take a zoom into the nearby points, you will see that it will be very, very small distance difference between the plane and surface, which we can, in the next part, we can see that we can approximate these two planes, the plane and the surface, with some approximation. So we can approximate a function of 2 variables with a plane equation. Okay. Remember that you have a curve in calculus 1 that can approximately take approach with a line. Now you can take approach with a plane. Very similar concept. Very similar. Remember that you have the curve like this, right? And suppose that you have a point here and you have a line. And you see that this is quite a large gap, but when you get into nearby this point, let's say this one, you see this small gap here, right? And you can actually approximate this blue curve with this line as long as it is nearby this x, nearby this point here, right? Same thing we can do for this part here. We can approximate the surface as long as we are in nearby this point 113, right? 113. So this is nearby 113. Maybe the difference can be in decimals, maybe 0.0 something. That is quite small that it can be approximately the same with the surface. So this plane equation, in terms of linear approximation, can be used as our linearizations for the surface. So if we take some numbers that is going to be nearby this 113, it means that we can find for some x and y that is nearby that point, what will be the z? That is something that we could actually approximate, and it will be not too much different from the real functions, the surface function. Okay, so let me write here linear approximations. So suppose that the for fxy that is equal, this is the last equations. at 0.113, the plane equation is z equal 4x plus 2y minus 3. So in the visual evidence that we zoom in the point, we see that this is actually, we can write as a linearization of two variables x, y. So this, we can say, is good approximations. To fxy when the point is near 1, 1. This L we can also call as a linearization. Linearizations of f at 0.11. And we can say the approximation to fxy approximately is 4x. Literally, they are the same thing, but different, slightly different definitions. This we call as linear approximation of tangent plane oh wait, wrong, or tangent plane of f at 1, 1. So if we take some nearby points, for example, at 1.1 and 0.95, our approximations will give you 4 multiply 1.1 plus 2, 0.95 minus 3. And if you compute this, you will get this result is 3.3. And if we compare to our functions, so this is approximation, so this is approximation, but the function this will be 2. This is our functions. This is equal to 3.3225, which is not so far away from. So this 3.3, our approximation, is not too far away from the real number at this 1.1, 0.91. But if we maybe take some points that is going to be far away from the 1, 1, maybe 3, 4, or maybe 2, 3, the result will be far away. Okay. So as a maybe perhaps as in the expressions here, we can express the approximations So this is called linear approximation or tangent plane approximation. Of f at AB. Okay, practically, if you see what we have here, this is actually the same thing as our tangent plane equation. We put this into this will be the z, right? And this will be the same as we did before the tangent plane equation. The difference is if we take some part of the, let's say the point, so first we set up any AB that easily to be described, easily to be computed, okay? And then we choose some xy that is nearby the AB. Or maybe the question would be start from xy, maybe 1.1 and then 1 point, or maybe 0 point something. It means that we need to find any number that is easily to be counted nearby that number of the decimal, which may be giving you the idea, oh, maybe we can take 1 and 0. So at this 1 and 0, we can easily compute the tangent plane, and then we can just add the xy. Okay, so next part, okay, before I give you some example on the linear approximations, let me write here. This is, I think, maybe the last part for today's class. So recall, this is the tangent plane equations. I will write only the partial x, but of course in the tangent plane, you need to input the point. And we have the linearizations of f at some point AB. Now I will put the z as Lxy, and then the z0, I will move to the right side and it will be FAB. plus okay. So this is actually z and this is z0. Okay. Now if z is function of two variables x, y, then f is differentiable at point AB, and if the delta z can be expressed as delta z so I will write in terms of delta for all the changes. And there will be some epsilon for each change for x and y, where this epsilon, these two epsilon, will approaching 0 as the delta x and delta y, or maybe let me write as delta x, delta y, going to be 0. So if partial x and partial y exists nearby AB and continues at AB, then f is differentiable at AB. Okay, this is the complete definitions for differentiable. Actually, you can take this as this form, which more simple if you want, but I think I keep this because you can see how much connections from linearizations to what we have here in differential form. And how this epsilon can be 0 is actually similar to what we have in calculus 1, okay, if you remember. In calculus 1, in single variable, we see that the delta x is getting 0, and that will affect the epsilon, that will be also 0. This happening for two delta 1 and delta x, which they can go to 0, and as implications, the epsilon will also be 0. But I think the last part here is quite important. So if you know that there will be exist partial x and partial y nearby this AB, it means if you can imagine the way we zoom in the surface at some certain point, and they are continuous at the AB, we can just simply say that they are going to be differentiable. I think I will just stop until here. The next part will be maybe overview and the chain rule. Okay, that will be for next week. Chain rule and the differential derivative or directional derivative.